Hello, my name is Eduardo Pavés, and I will be presenting our paper Compression of User-Generated Content using denoised references. This is joint work with Enrique Perez, Xing Xiong, and Antonio Ortega at USC, and Balu Absumili at Google. I will start by going over the compression challenges for UGC, and I will then give our rate distortion theory perspective of this problem. And using this theory, I will propose a practical UGC compression approach that uses denoisers. I will end with experiments and conclusions. The majority of the videos shared over the internet is user-generated content called UGC. This video is diverse. There are many types of UGC video, and it also comes in different quality levels due to many factors, including camera shake, low light, and in particular compression artifacts. Typically, a UGC video is basically created, and then it's compressed and uploaded to a video sharing service such as YouTube or TikTok. And then this video is recompressed at multiple resolutions and at multiple qualities. Now, if you have a traditional video that has high quality, like the one on the left, a traditional video coding system will try to allocate bits and to preserve all the image details of this content. While if the input is a low quality UGC video, the details correspond to noise and artifacts. So the main challenge or the problem of the UGC video is that we want to avoid spending bitrate on these undesirable noise and artifacts. Now, if we were going to compress a pristine input as a traditional video coding, we would, let's say, have a target rate R. The encoder will optimize its parameters, and then at the decoder, we get a reconstructed signal X hat. We can measure the quality using mean square error between X and X hat. And if we plot this as a function of the rate, we have this decreasing curve. And as we increase the rate, the mean square error goes to 0, and X hat converges to X. And we know that because the input is pristine, then as we improve the rate, the quality also improves. Now, if we use this system to compress a low quality UGC signal with the same target rate R, we need to compute the mean square error between U, the input UGC, and U hat. But we are actually ignoring the fact that the UGC signal has been degraded. And there's a degradation process and an unknown pristine original that we don't have access to. Now, we can plot this MSE as a function of the rate. And as before, as we increase the rate, the square goes to 0, and the UGC, encoded UGC U hat converges to U. Now, if we look at the encoded UGC using non-reference perceptual quality metrics, we observe a different phenomenon, which is basically that at the beginning, at low bit rate, as we increase the bit rate, the quality improves, which is shown here by a decrease in risk. And then after around 29 kilobytes, if we keep increasing the bit rate, the quality gets worse. This phenomenon is also observed for other quality metrics. And basically what happens is that there's no perceptual quality improvements for rates beyond 29 kilobytes, at least for this particular example. So in this work, what we propose is a method to define this transitional saturation point, and a method to detect it, but during encoding and using only mean square error. And thus we avoid using perceptual quality metrics. Basically, how to find this line here. What the saturation point is important, it's because at this rate, the quality of the encoded UGC and the quality of the input are comparable. In terms of rated work, we consider two groups. One of them are non-reference metrics, and the other one are the classifiers or rate distortion and content type. What all these methods have in common is that they're either applied before the encoder or and after the decoder. So they're out-of-the-loop methods, and they also require a training. So the goal of this work is basically a definition of the saturation point, and then how do we use this saturation point during the encoding process. And this is different to previous work that works before the encoder or after the decoder. We seek methods that are in loop. On the theory side, we understand the fundamental limits and differences between UGC and traditional video coding. And on the practical side, we propose a technique that reuses existing video coding. And it's basically complementary to existing tools based on non-reference metrics and classifiers. The main idea is a change of distortion. So let's go back to the traditional diagram that we had before. The traditional approach would compute mean square error between U and U hat. In the ideal case, we would like to compute distortion with respect to the pristine original. Of course, this is unknown. That's why this is an ideal scenario. And in a more practical scenario, we may have access to a better reference that's available. Okay. So in this work, we're going to provide some theory that compares the traditional case with the ideal case. And then we propose an alternative practical method that uses denoising to compute a reference C. Our first result is based on a traditional source coding formulation where the optimal rate distortion function is the one that minimizes the distortion subject to a rate constraint over all encoder F decoders G. Now, for UGC, we consider an alternative distortion that uses the pristine original as reference. And again, it minimizes over all encoders F and decoders G. And if we invoke a classic result from information theory called the noisy source coding theorem, we have that the optimal distortion function can be decomposed as two terms. The first term is a constant plus an optimal rate distortion function that encodes the conditional expectation of X given U. This conditional expectation is actually the minimum mean square error estimator of X given U. And this second term here is a traditional source coding, but that encodes this denoise signal. Okay. So in a nutshell, the noisy source coding theorem tells us that you take the UGC signal, you apply optimal denoising, and then you encode this optimally denoised signal using an optimal source code with encoders F star and G star. What happens is that the first, in a previous result, the first term corresponds to the error of the optimal denoiser of the MMSEE. The second term is the distortion of the optimal source code at rate R. And because both terms are non-negative, we can lower bound this by the error of the optimal denoiser, which we call D0. And this distortion is actually achievable because as we increase the rate, the second term, the sum goes to 0. So this the error of the optimal denoiser corresponds to the best performance that can be achieved. And differently from traditional compression, here the distortion does not go to 0 and goes to a positive value, D0. Now we show an example using Gaussian sources. So we will consider X and nu as Gaussians that are independent of zero mean. We will encode, we show that encoding the pristine X will reference X in the red line that goes to distortion 0 as we increase the rate. We also show that we can encode the UGC signal by using U as reference. And this is the blue line, which is basically using a traditional system. And then we have the ideal UGC coding, which encodes U, but the source is X, and the optimal rate distortion function is the black line, and this converges to the constant D0 as we increase the rate. And it, of course, doesn't go to 0. Now, how do we use this result for a practical method? So basically, optimal denoising and optimal source coding are never available. So therefore, this system is not realizable because we cannot compute the denoiser and we cannot encode it, of course. So what we propose is a solution that is inspired in this approach. What we do is we replace the optimal denoiser by a practical denoiser that we can get using off-the-shelf algorithms. We also encode U instead of DU. One of the reasons is that the users expect their video to be uploaded to the internet, not a denoised or modified version. And then we use a traditional compression system, for example, JPEG or AV1. And the way we use the The denoiser is to change the distortion. So we compute distortion with respect to the denoised UGC. This denoised UGC saturates. So we show an experiment here where we generate a synthetic UGC using a compression algorithm. We re-encode it using JPEG, and as denoiser, we use BM3D. We compute the mean square error for each block, and we discard the largest 25% and the smallest 25%, and we use the MSE interquartile range, which is a robust measure of error. And as we can see, when we use the denoised reference or the pristine reference, the interquartile range MSE goes to 0 and about the same range, same bit rate. So they both saturate similarly. Now I'm going to describe a little bit about our saturation criteria. So let's X is the pristine signal and U is the UGC signal. There is this region that is not, we cannot approach it because it's within the error of the optimal estimator. So the denoised UGC is going to be outside of this region. And let's say U hat is a low bitrate encoding of the UGC. So as we increase the rate, the encoded UGC will approach U, right? But we don't want to increase the bitrate until we reach that point. So what we define is this notion of noise encoding region, which basically compares the encoded UGC to both the denoised reference C and to the input UGC. And we define that we are encoding noise when we are closer to the UGC than to the denoised reference. Therefore, the noise encoding region are basically the blue points on one side of this line, and the region in which we want to operate are the ones, the yellow points, and it's in the other side of this blue line. Now, I'm going to describe our experiments of detection of the saturation region. So we will denote by UIT and CIT, both the UGC and the denoised UGC of a block I and frame T. We will consider several quality parameters QV that are used as input to JPEG. QVN, which is the largest value, gives the highest quality, the highest bitrate. And then U hat ITN is basically the encoded UGC of block I, frame T, with parameter QVN. And we say that this block is saturated for this parameter if it is closer to the UGC signal of the block than to the noise signal. And then we collect this in this set of scalars delta ITN for each block, for each frame, and for each quantization quality parameter. Then we define the saturation quality for UIT as the smallest quality value that for every quality value that's higher, all the blocks are saturated. So basically, once we have reached saturation region, increasing the bit rate keeps us in the saturation region, and we want to find the smallest quality value that has this property. And then the saturation quality of a video clip is basically the median overall frames and blocks. In this next experiment, we display the optimal saturation value for the clips on the UGC dataset, and we compare them with the mean opinion score, which is a perceptual measurement of the quality of the video. And we observe that higher quality videos, which have higher MOS, our method tells us that they can be encoded at higher qualities or using higher quality values. As a conclusion, we are the first to formulate the UGC compression problem using array distortion theory. We show that an ideal UGC system is comprised of optimal signal denoising followed by optimal encoding of the denoised signal. We show that beyond a certain point, increasing the bitrate does not really lead to an improved quality of the UGC. And inspired by these theoretical results, we propose a practical system that reuses compression infrastructure and combined with off-the-shelf denoisers to guide the encoder so that undesirable artifacts and noise are avoided. This proposed framework is complementary with respect to existing non-reference metrics and classifier techniques that are used before encoding or after decoding. Thank you. I would be happy to answer questions over email.